Welcome to this extended version of the talk that I'm going to give tomorrow at the TLA tutorial at DISC. So this extended version is meant to be more like a dev session or a seminar, so you're free to ask questions. And I urge you to ask questions actually, because there may be some typos and problems with this presentation. And this extended version will upload it on the web page, on Apalache web page. So the attendees of the TLA tutorial can watch it later to see more details about the talk. So you don't have to download this material that is shown on this slide, but if you want to follow along and check the specs, the source code, you can go on this URL or scan the QR code if you're using a smartphone, I don't know, and check the specs. Again, it's not like a prerequisite, it's just if you're interested, or you can do it later. So let's start with Apalache. This is a rather short tutorial, so I'm not going to give you all possible ways to use Apalache, but I want to give you some intuition about when Apalache is efficient, when it's not efficient, and to give you some ideas about symbolic model checking. So to start, you can go on the Apalache website, apalache.informal.systems. You can check the documentation there. And if you want to run the tool, here are the commands you have to initially do if you want to run. What you have to do, you have to download Docker, unless you want to compile this thing yourself. And then you pull the corresponding image, set up the alias. I'm assuming that you're using Linux or macOS. You set up the alias, and then you can run the tool. And in the course of this talk, I will give you some commands in this interactive mode that show how you can check invariants or how you can just run the tool in some meaningful ways. So you set up this alias. It's a lot to type, but it's all in the manual. And then you can run the thing. So there are many TLA specifications around. You can find a lot of them on the web. I actually wrote a new specification of a clock synchronization algorithm. And the reason why I used this one is because I think it actually highlights the strong sides of Apalache. And I hope I will show you why. So let's talk about clock synchronization. What is clock synchronization? I consider this classical problem from distributed computing. You have several computers, they have the hardware clocks, and these hardware clocks can actually differ from each other. They can differ from some of the global time, which they don't know. What we assume here is that they can drift, but they cannot change the clock rate. The clocks all have the same rate, so although the values are different, they progress at the same rate. So the point of clock synchronization is to design an algorithm that actually allows different machines, different computers to exchange these messages, so that by the end of this algorithm, or by the end of this communication, they adjust their clock values in a way that these clock values are probably not equal to each other, but they're not so far apart from each other. So that's clock synchronization. In the end, we want to access these variables AC1, AC2, and AC3 on each computer and see the adjusted clock value, which is not so far apart, not so far from the adjusted clock value of another computer. So basically, the goal of this algorithm would be to compute these values AC for each processor, for each computer, so that the difference is smaller than some epsilon. And epsilon actually depends on the number of machines, or depends on your setup. So the algorithm should tell you what this epsilon is about. So any questions about clock synchronization in general? anything not clear here or any comments? Okay, let's continue. So if we open the book, say the book on distributed computing by Hagit Ati and Jennifer Welch, we will find this rather small algorithm that tells us how to do clock synchronization, assuming that there are no faults and the clock rates are not different, right? So that's a rather simple algorithm, although the reason about it, it's not so easy. So what happens in this algorithm, you have the variable that collects the difference between the clocks of different machines. At first computation step, every machine, every processor sends its hardware clock value because it only knows the hardware clock value. And upon receiving a message, the a processor computes the difference between its own hardware clock value and the value it has seen in the message, and also takes into account the maximal and minimum message delays. So this algorithm assumes that messages are received within some time window, right? Once it has computed the difference for all processors that are different from the processor itself, it can compute the adjusted clock value. It just takes the sum of all differences divided by n. So it's like, it looks like a very simple algorithm, right? It might take some time to understand what's going on here, but it's only 6 lines of pseudocode. And that's the algorithm I want to specify and model check with Apalache. So basically the rest of this talk is about how we are going to turn 6 lines of pseudocode into about 170 lines of CLA+. Of course, if you come from distributed computing, this looks horrible, right? You had 6 lines of pseudocode, they tell you what's going on. Why should you write that many lines of CLA+? So the important thing here that these 6 lines of pseudocode assume that you have read 9 pages of mathematical text in the textbook, which explains to you all the things about the clocks, the adjustments, the delays, the message delays, and other things. So it's not only 6 lines of pseudocode, it's all information that actually precedes the 6 lines that you have to understand. And this all will be in CLA+. Let's start. So basically what I want to do in this talk, I don't want to give you a complete specification right away, although people often do that. I want to show how you can incrementally design such a specification and check some useful properties while writing down this specification. Because a common problem is that people write a specification before they even try to check it or before they even try to parse it. And once they're done with the specification, they have so many errors in it, it's very hard to debug. So a more productive way, as we have found at Informal Systems, a more productive way is to incrementally write your specification, add properties, check these properties, and go forward with this extended specification. So in version 1, I'm not going to have the clock synchronization algorithm. I just want to set up the clocks that we are talking about here. And this is that's the whole specification that you see on your left. I just show the most important part of it here. Basically what we do here, we introduce a state machine that uses integers. And this state machine will have 3 kinds of variables in each state. It will have the reference clock, that's a global clock that the processes cannot read, it's just some kind of global time. It will have a hardware clock, 1 hardware clock per process. That's why this type annotation here, we also have type annotations, and this type annotation here says that it's going to map the name of a process to its clock value. So IHC is going to be a function. And we also have the variable called adj, adjustment, which is also a function from the process name to the clock value. So we have these three variables, and these variables are going to evolve over the time. With every step of the system, they're going to evolve. How can they evolve if you just have clocks and nothing else? Well, so yeah, we also introduce this additional auxiliary definitions like the set of all processes. In this case, we just have two processes, P1 and P2. And we also define what it means to compute the adjusted value. We basically take the sum of the hardware clock and the adjusted value for this clock. So how is the system working? We initialize the system with some time for the value for the time, and this value is just a natural number, as you see here. We also say that each process will have a natural value assigned as its hardware clock value. And here we don't assume much. We just say these are some values. We don't know what they are. We don't even write down any relation between the hardware clocks of different processors, and we even don't write any relation to the global time. The only thing that we know for sure is that this value of the adjusted clock is equal to 0. So the delta that we are going to compute is equal to 0 for now. That's how we initialize our machine, our state machine. The next thing is that yes?
One question, if you can go back to the previous slide. Yes. So in the type annotation for time and for HC, you mentioned the int type.
Yes.
Comes to natural numbers, I guess. But in the initialization of the variables, you mentioned the nat set. Right? Can you tell us why those are not? So it's not nat in both cases, or it's not int in both cases?
So that's a very good question, and I guess many people would say I should put nat here, right? In Apalache, our type system is rather simple. We basically, the main goal of the type system is to map TLA plus into the series that are supported by logic solvers, by SMC solvers. So we don't have nat as a type. We don't have natural numbers as a type. We just have integers. But in TLA plus itself, you can use the set of natural numbers. It's a set, right? So when we write that time belongs to nat, it actually means that time should have the integer type. But on top of it, we'll add the constraint that time is greater or equal than 0, right? So it's greater than 0 or equal to 0. I think it's really as simple as that. We probably could extend the type system to differentiate between naturals and integers, but it doesn't look like we need it at this point.
Yeah, and if you're doing that, then you would have to prove that, for example, subtracting two natural numbers would also yield the natural numbers, or what? I mean, opens a whole lot of worms, right? So here, I guess it's just enough to say that the time is just an integer, and then in the actual spec, you just refine it by saying, the actual values are going to be natural numbers at this initialization. Makes sense. Thanks.
I mean, it's always this question, way you want to reason about the shape of the values, right? And in principle, in TLA plus, if you're using TLC, you don't specify any kind of types. You just say what kind of values a variable can hold. Usually you would write type OK that just gives you this shape. So we have to be more precise because we have to map these constraints to SMT formulas, to first-order logic. That's why we have types. But again, it's always this question, why do you want to reason about it? If you want to reason about it before you run this solver with some advanced type checking techniques, then I guess in the end of the day, you might even start using the solver again to do type checking. We just use the solver to do model checking, not for the type checking. I think that's a border, right? Whether we want to use advanced proof techniques to reason about types or not, and we don't. We just use SMT techniques for reasoning about models. Yeah. Good. So please ask more questions. That's a good one. So yeah, so that's how we initialize the system. What can we do here? What kind of actions can we perform if we just have clocks? Obviously, there is just one kind of an action you can do here, and that's advancing the clocks. What we do here, we say that our transition relation, which is called next, just by convention, looks like this. You pick some delta, an integer, right? And again, it could be natural, but just write an integer here. You pick a delta, and you say that the clocks should advance by this delta. What does it mean that they advance? Here, I put this precondition that delta is greater than 0. The global time is getting incremented. The global clock is getting incremented by delta. And all hardware clocks are getting incremented by the same delta. So you see, the clocks are moving uniformly here. And that's it. So that's the whole specification that we can have here if you just want to specify the clocks. There is no synchronization, nothing, just about moving clocks. However, even this small specification is useful. Why is it useful? You can run the model checker. You can make sure that your specification parses, that it's syntactically correct. You can make sure that it's type correct, the type checker doesn't complain. And you can also do some kind of basic debugging here. Say, if the model checker complains that it cannot find any transitions out of your initial states, it's already something you should think about. And here's how you can run it. Just an animation that shows how to run the tool, basically. So that's a very basic specification. However, this basic specification allows me to explain in a very simple way what we mean by bounded model checking and symbolic model checking in general. Because it's so simple, I can give you all these details here. Basically, if you look at this specification, the only thing, as I told you, you can do is only incrementing the clocks uniformly, which gives us this idea that instead of trying all possible executions one by one and trying all possible states, which are infinitely many, you can write down a series of equations that tell you how the clocks are actually evolving over the time. And that's basically a symbolic execution. So you say that in the initial state, your time variable is initialized to 0. The hardware clocks are initialized to some constants. They're integers, you don't know what integers they are, but there's some constants, right? So different executions will differ in the value of these constants. But we can write down the whole execution as a set of these constraints. So the adjusted clocks are equal to 0. In the next symbolic state, or in the next frame, as we would call it, the clocks are advanced by some delta 1. Delta 1 is a constant, again, is an integer constant. You have to find one. You don't know which it is. It depends on the concrete values, but it's a constant, right? So you see the clock values are actually getting increased. We also have to say that deltas are actually positive. I don't say it here, but it should be here. So the clock values are getting increased, and basically all executions you can imagine in this system, in this specification, they look like this. You just have to instantiate the values for delta 1, C1, C2, delta 2, and so on, delta 10. So this is the shape of every execution in this system, of every execution of length 10. You can extend this execution to be an execution of length 20, and so on and so forth. But the interesting thing, that's the only execution you have, in some sense. So frames or symbolic states, they represent multiple concrete states that correspond to different values of clocks and deltas here. So that's a very simple concept, right? If you're talking about this simple specification. If you have a more complex specification, of course, it's getting harder to understand what's going on, but that's the beauty of this example. It's very simple, right? So what we want to do, we want to reason about this symbolic execution in some way without enumerating all possible states and without enumerating all possible executions. And that's what bounded model checking does for us. So bounded model checking is a set of techniques that basically allow us to reason about symbolic executions without evaluating things, but by solving a set of constraints, the help of advanced SMT solvers, for instance, Microsoft Z3. So if you look at the set of initial states, at the initial predicate that we have, right, what does it tell us? It tells us that there are a few constraints here, right? So time is initialized with 0, hardware clocks are initialized with C1, C2, and the just clocks are initialized with 0. You write down this set of constraints, not we, actually Apalache does it, and it asks the SMT solver, Z3 in this case, it asks Z3, is this set of constraints satisfiable? And Z3 says, yes, here's an example, here's a model. And Apalache says, great. So I know that I have found at least one initial state. I can go on and do a step. Then it writes down, Apalache writes down a set of constraints for step 1. It adds them on top of the set of constraints for the initial states and asks Z3 again, is it satisfiable? And Z3 says, yeah, here's a model. And Apalache says, great, I could make one step. Maybe I can make 2 steps. Again, it adds constraints for one transition, for one symbolic transition, advanced clocks, and asks Z3, is it satisfiable? And Z3 says yes. So we continue like that, and as we have seen before in that terminal, it just keeps incrementing the length of a symbolic execution, and it's asking Z3, is it possible to extend this execution? Z3 says yes, and at some point we terminate because we have constructed a long enough execution. In this case, an execution of length 10. We could construct a longer one. So basically, that's a very, very, very rough idea of what's going on in Apalache. That's what we call symbolic exploration. And by default, it doesn't do much, actually. By default, what Apalache does, it finds enabled actions at each step. In this case, it's advanced clocks. If there is just one action, it immediately adds constraints about this action and continues the next step. If there are more than one enabled action, and we'll see that it's possible in the next examples, it would just add a non-deterministic choice between the results of one of these actions and continue with the next step. When it has constructed a long enough symbolic execution, Apalache terminates and says, look, I haven't found any problems. So just to give you some intuition about symbolic states, because it's always a question of what symbolic execution is about and what symbolic states are about, here is a picture. Basically, you have these balls or this complex complicated geometric shapes. They describe a set of states. Then you have this cylinder, which is a symbolic transition or a part of or an action in CLA+. It computes another ball, and so on. You apply another symbolic transition, it computes another ball. So you're always talking about some sets of states instead of talking about individual states. And in case you have several actions, you actually have a choice of how you transform these balls by firing one of the actions. So that's a very, very rough intuitive idea here. It's good to have it in your head because it's a bit different from explicit state enumeration as you usually would see in TLC. What's important here is that if you're talking about this set of constraints that we have seen before, we have infinitely many solutions to these equations, which means that we have infinitely many states and infinitely many executions. So that's very important to understand that in general, if you're talking about symbolic execution and symbolic model checking, cannot just enumerate things one by one. Of course, Apalache has some assumptions. It deals with bounded data structures, but we can have integers. So let's continue here. We haven't done anything useful. We just constructed a symbolic execution until now. assume we want to check some candidate, invariant candidate. We want to check whether some property holds. In this case, I write a very stupid property, which says that the adjusted clocks of all processes are equal to each other, right? And of course, it's not true, but I just want to check whether it works or not. So I write down this invariant candidate, and what Apalache does, it first constructs the constraints for the initial states, and then it adds the constraint that actually there is a typo. It actually should negate this invariant. So it adds the constraint. So yeah, what we do here, we check that whether it's possible to violate the invariant. So it shouldn't be equality here, it should be an inequality. Then we run the solver, and here's how I actually run it. I run Apalache, I just say check this invariant, which is called naive skew invariant, and I pass the specification. And then after a few seconds, Apalache says, this invariant is violated actually, and here's an example where one clock is equal to 0 and another clock is equal to 1. A very simple example, right? So we didn't do much, but we see that our simple specification is working. Apalache is finding some counterexamples, so we can continue. But actually, what I have found very productive and useful that instead of immediately extending your specification with more actions, you should write a test. And this test will test the single action at one's clock in isolation. What kind of test can you do here? Actually, you can test something here. You can you can say that you start in an arbitrary state where global time is a natural number, the hardware clocks are set to some natural numbers, and clock adjustments are set to some integers. Then you fire advanced clocks once for some delta. And there is a property you can check here. You can actually check that your clocks are not decreasing. It's not a very complicated observation, but in this specification holds true. So I think it's a good approach actually when you write your action and you still have it in your head. It makes sense to write a couple of simple tests like that actually help you in debugging the specification when the specification becomes large, and also it helps you to compute inductive invariants in the end. But we'll not talk much about inductive invariants. Okay, so let's try to send messages. This specification doesn't do much. Let's try to send messages. What do we have to do to send messages? First of all, we have to introduce two constants like tmin and tmax here that tell us what is the minimum and maximum message delay. Also, we have to write some constraints about them by saying that tmax shouldn't be below tmin, for instance. We introduce more state variables. One of them will hold all the messages that are sent by processes. And we also introduce the variable which is just called state. It will tell us in which state each process is. So initially it's the initial state, and then it will be sent state or synchronized state. So we added two variables. How do we send messages? I add this new action here, which I call SendMsg. And it can fire for any process as long as this process is in state init. Upon firing this action, we add one message into the set of messages, which says who has sent this message, that's process P. And we also put the timestamp, which is a hardware clock, the value of the hardware clock of process P. Once we have done that, and actually it happens all at the same time, actually, you update the state of the process to be equal to send, just the name. And the other things are not changing. The clocks are not changed by sending a message. So in this case, we have two actions. One of them is advancing clocks, and another one is about sending messages. So now we write in our specification that you can fire one of these actions as soon as one of them is enabled, right? And now Apalache will have to choose at every step which action is going to be fired. Apalache by itself doesn't choose the actions to fire. It just tells the solver, here's how you choose an action, one of the enabled actions. And the solver has to do all this work. So again, we have this send message action. How do we test it? We create a new module, which is usually called MC something, MC clock sync 2. Here I put some constants for tmin and tmax, just to know, just not to try different constants. I tried the fixed ones. And I also describe this shape of the states I want to test against. Now it's getting a bit interesting because not only we have to say that time is natural and HC is a function from processes to naturals, I also have to describe messages. And here I have to play a bit because Apalache doesn't accept all kinds of constraints. Here I have to say that I non-deterministically pick some kind of timestamps, basically a function from processes to integers, and say that messages are a subset of this set that contains all possible, that contains all records that have P, a process P as a source, and the timestamp from T of P. So in general, in CLA, you could write it in a more compact form, but here we have to play a bit because Apalache can reason only about bounded data structures that have boundedly many elements. So we have to write it this way. So we write this type init, and we write another test. We say, here's an invariant I want to check that for all processes, if a process is in state send, then indeed there is a message where process P is a source. Again, I write the initial predicate for this test. I say that the only transition that I can make here is sending a message, and I want to check that the invariant holds true after firing this action send message. Here's just the command. You can see how it's working, but basically this test goes through. Again, we have some useful piece of information. We don't have a complete spec yet, but we already can do something about this spec. How do we receive messages? This is getting interesting, right? Again, I have to add one more variable, which will contain the received messages for every process, and that's a function from process names to sets of messages. And then I add one definition. No, I add two actions here. The first one is receiving messages, obviously. And here I'm saying that whenever there is a message in a set of messages, and this hasn't been received by the process P yet, if the timestamp in this message plus tmin is larger than, is smaller than, actually smaller or equal, less or equal than the hardware clock of the process that has sent the message, then we can deliver this message now. And in this case, I will add this message into the set of messages received by the process P, right? So in this case, I cannot hand wave and say I just receive a message. I have to tell the model checker, I have to write in the specification that I cannot receive a message earlier than tmin after the moment the message has been sent. This has to stay explicitly somewhere, maybe in this section or somewhere else, but it has to be written. Now we also have to update the advanced clocks because we're receiving messages. And the important update here is that we cannot advance a clock beyond the point when some messages cannot be received anymore, although they should have been received. So we have to write this constraint that is saying that if you are advancing your clocks by delta, then all the messages that must have been received after Tmax are already received. If it's not the case, you cannot advance the clock. So advancing the clock becomes a bit harder here. And we can argue whether it should be in advanced clocks or it can be another piece of the specification. but this constraint should be somewhere, and we have to write it explicitly. So this is getting interesting. Now I can write yet another test. I'm not going to explain you what it's doing, but basically it's doing these basic checks that messages are not received before tmin or after tmax, or you don't have messages from the future, for instance. Again, we run the tool. It takes 6 seconds to check this test, and it kind of works, right?
I have a question here.
Yes.
So like that check, which is basically telling that you cannot advance the clocks if the pending messages aren't received within like tmax, like I'm not able to like relate like that to where it is specified in the algorithm.
Oh, you mean in the algorithm, the pseudocode algorithm?
Yes, yes.
That's a very good point. In the pseudocode, it's nowhere specified, right? In order to understand, that this constraint is indeed required, you have to read the 9 pages before this algorithm, because there it will be explained that there are the minimum delay and the maximum delay that you use to send messages. It's a very good point, because usually when you see the pseudocode, it's not clear, right, how you send messages or receive messages. That's usually what is called bookkeeping, right? Of course, if you write your implementation or write your specification, you have to be clear about it. In an implementation, you probably can also say, okay, I receive a message at some point, and my assumptions are that, you know, I receive messages in time. But in the specification, you really have to be very precise about it. And I mean, you have the specification, you can actually remove these constraints and see how things start to break apart, right? Especially if you want to check the invariant. But it's a very good question. Thanks. Is it clear now? Or?
Thank you. No? Yes, I understand.
Oh, perfect. So again, we check this test, and here something is going on here, right? It's not a trivial specification anymore. We have some properties, not very complex, but again, it's very useful to write these tests. Okay, finally we can finish our specification. Now we can say what it means to adjust the clocks. And here I have to extend the section for receiving messages. Here I have to add a bit more details that you can see in the pseudocode, actually. What we have done before, basically the whole thing was outside of the pseudocode. Advancing clocks, sending messages, receiving messages was kind of bookkeeping, right? But you have seen like the largest part of the spec was about this bookkeeping. Now we can do the meat of this algorithm, right? What we say here, when we receive a message, we actually compute this delta between the hardware clock of me and the hardware clock value that I have seen in the message. Then we take the average between, too much. Then we take the average between tmin and tmax, and we update this diff variable that we have seen in the pseudocode. If we have received enough messages, basically have received messages from all processes, we have to compute the adjusted clock value. Here I just give you an example for 2 processes because it's a bit hard to write. To explain how we sum up things, I just sum up 2 values here. And you can see an extended specification in the source code that does it for in processes. So basically here I compute how the clocks are adjusted according to the pseudocode, but in a bit more precise manner. So that gives us a more or less complete specification. It captures all the system behavior plus the algorithm, the clock synchronization algorithm. Now we finally can stop writing tests. We can specify what it means to have bounded clock skew according to the book, and let the model checker check it, right? So I write here that first of all, I write what it means for all processes to be in the state sync, right? So what I want to check is that if all processes are in the synchronized state, then for every pair of processes, the difference between the adjusted clocks satisfy this constraint. And basically, I have to play here with multiplications because I'm not using rational numbers as in the book or real numbers. I'm actually using integers. So that's why I have to write things in a bit less straightforward manner. But it basically encodes this fact that the difference is between minus epsilon and epsilon, where epsilon is computed like this, divided by the bound. Yeah, so that's the property you want to check. And if you run the model checker, there are two outcomes. Either it works for some lengths or it doesn't. And I'm not. I haven't invented this bug. There is actually a bug in this specification, and I did it by accident. Apalache says there is a counterexample. I looked at the spec and the pseudocode, and then I looked at the counterexample. And what happened here is that the processes themselves are adjusting their own clocks. This is kind of unexpected, right? Why would a process adjust its own clock? It knows it precisely. So the reason for that is that I missed this line that is saying that I should receive a message from every other processor, which means that I shouldn't calculate adjustments for myself. I should exclude the process P, actually. So that was a bug which I made unintentionally, actually, and the model checker has found it. It's good. I'm not going to show you the fix. You can check this specification clock sync 5. And here, what happens now this counterexample doesn't show up, but we have to wait. You see, I have to wait for about 3 minutes. And after about 3 minutes, the model checker told me, look, I couldn't find any violations of lengths 10, which is good. Our specification is doing something. The question is, of course, how much can we trust this result, because it's not about infinite computations and some parameters were fixed. So you might want to ask this question, what about the constants Tmin and Tmax that tell us what are the message delays? I have used fixed constants, which was good for debugging. What about the general case? Actually, in Apalache, we can say that we want to check the specification for arbitrary values of Tmin and Tmax. For that, we would usually write a predicate over constants. Of course, there are some limitations here, but in this case, you can write that they're just arbitrary naturals, and let Apalache check this the specification for arbitrary values of Tmin and Tmax. What's interesting here, there is another bug, which is not the bug in the original algorithm, but this bug is here because I used integers. So there are some small rounding errors because I divide by 2 or by n, where n is number of processes, which means that my clocks are a bit off, they can be outside of this bound that I can see in the book. Well, I solved it easily just by increasing the bound a bit, by basically the value of n. Here I have to do this multiplication because I'm doing instead of division multiplications later. In principle, I could use rational numbers instead of integers, but that would make the specification harder to read. That's why I didn't do it. So you see, even in this simple specification, I have found 2 bugs, basically because I was sloppy. I guess if I stared at this specification for a long time, I would have found these bugs myself. But I didn't have to because the tool found the bugs for me. So that's another fix. And this basically finishes this short, intuitive presentation of Apalache. The question is, what can you do next? Well, what have we done now? Now what can we do further? And that's what I did. I actually parameterized the specification by a set of processes instead of just having 2 processes. When you run Apalache, you still have to fix your set of processes. You cannot say, I check the specification for an arbitrary set. You still have to put some bounds. But the specification itself is actually not fixed for this set of processes. So you can use a prover, for instance, the TLAPS proof system to reason about the specification. We have checked 4 unit tests, and actually I could have written more unit tests. It's also useful to have them because usually you debug your specification in the initial stages and you learn something about your specification, but then you forget it. Like engineers write unit tests, we actually should write unit tests for specifications. That's quite useful. I could check the specification for short executions of 2 and 3 processes. You can check it for arbitrary values of Tmin and Tmax. Of course, you should keep in mind that the bound had to be extended a bit. But what we see in general is that the more processes we add, the longer executions we use, our otherwise very fast tool becomes much slower. What can we do about it? Well, you can say that every tool has a limit, and that's true. So another thing that we can say here, and we can try to check an inductive invariant instead of trying to shoot symbolic executions of length 10 or executions of length 20. I'm not going to tell you how to check an inductive invariance here. It's I think it's a subject for one more talk, but I just give an idea here. Basically, what we want to do, we want to find another predicate over states that has these 3 important properties for us. First of all the initial states are inside of the set of states captured by this inductive invariant. Second, if you take a step from a state that is inside this int-inf, you end up in a state that again satisfies int-inf. And third, whatever, and that's actually, I guess this picture is wrong. Actually, this green area should be larger. Actually, all states in the set that satisfies int-inf, they should satisfy the property you want to check. They should satisfy skew-inf. So that's basically an idea here, and we do check an inductive invariance with Apalache. The good thing about inductive invariance that they're relatively shallow in comparison to bounded model checking queries. They're much shorter in terms of length, and that makes Apalache fast again. So maybe one day we talk about it. I think that finishes my talk here. What you can do, you can go to the Apalache webpage. If you have any problems, just post issues on the GitHub. We have a Zulip channel set up at Informal Systems. If you have questions, please feel free to ask. We have some debugging sessions in Zulip going on. That's basically, the tool is still in development, so there are some bugs expected, and we know plenty of bugs. But the more people try it, the less bugs we have. And we are happy to work on this stuff at Informal Systems. Basically, bringing verifiability to distributed systems and organizations in different ways. And how we do it, we develop tools for verification and testing. That's Apalache and model-based testing tools. And we also develop infrastructure for the Cosmos ecosystem for the blockchain projects. And this means that we're developing the Tendermint consensus, we're developing support for the ABC infrastructure, and we're developing the Hermes relayer. If you want to join us, drop us a message. This finishes my talk. Any questions?